My goal in this video is to kind of give you a very informal introduction into the actual definition of a limit, which we don't ever tell you in high school mathematics generally. We usually kind of wait till you get to college and you do calculus, and that's when you get the real definition. But for now, I just want to give you one quick example to show you essentially what we mean when we're actually finding the limit of a sequence. So this says a function, or we could say a sequence, because the sequences are functions, has a limit, L, if you can guarantee that for any small distance, d, from L, you can find an input, E, large enough so that f of E is within d of L. So you might find it hard to believe that that's actually the informal definition, but the mathematical definition that's precise really is saying the same thing, but it has symbols instead of all these words. The first thing to point out is that I'm not using, even though the definition here has function notation, f of n, and I'm doing an example using a sequence. Remember that sequences are functions, so I could just view that a sub n as f of n or a of n if I wanted to, so hopefully that doesn't confuse you. The second thing is I know that you are all aware, if you were to just do this problem out, you'd probably just say, what's the big deal, right? 1 over 2 to the n goes to 0, so this clearly goes to 0 plus 5, which is 5. And you'd be right, but hopefully this example will give you a deeper look at what actually is going on here and why we can actually say that that is what the limit is. Okay, so in this example it says how large do you have to, just to kind of get these ideas going, it says how large do you have to make n to be sure that a sub n is within 0.1 of 5. So it's that language that I think is somewhat confusing for kids. So let's just decode that. We want to make a sub n within 0.1 of 5. So I'm just going to draw a number line here. I'm going to put 5 on it. And you'll probably notice that anytime you plug in a number for n, it's always going to be a little bigger than 5, right? So the a sub n is going to be, depending on the n, it's always going to be to the right of 5. Now for it to be within 0.1 of 5, we basically just need, so let's just say this distance here is 0.1. We basically need to be looking at the picture we're looking at right now, right? A sub n is closer to 5 than 5 plus 0.1 is, right? So we want to find how large do we have to make n to ensure that happens, right? So keep in mind that when you plug in 1 for n, it doesn't happen, right? Because you get 1 half plus 5, and 1 half plus 5 is somewhere over here. So clearly 1 will not do it. All right. So what we want to do is find the smallest n we can use that would make a sub n within 0.1 of 5. So we can actually turn that statement into a subtraction, right? A sub n is within 0.1 of 5 so long as you take the distance, this distance here. So a sub n minus 5 is that distance. We need that to be less than 0.1, which I'm just going to write as a fraction. That's a tenth. All right. And, okay, so what can we do with this now? Well, I'm going to just say that I'm going to add 5 to both sides here. So a sub n is less than 5 and a tenth. So how can we be sure that a sub n is less than 5 and a tenth? Well, let's just go put our explicit rule in for a sub n. So that's 1 over 2 to the n plus 5. So how can we be sure that 1 over 2 to the n plus 5 is less than 5 plus 1/10? And again, we could cancel out those 5s and be left with this. So it just boils down to, when is 1 over 2 to the n less than a tenth? And if you just follow these numbers here on the left, so I've got actually the terms written out. When is the first time that 1 over 2 to the n is less than 10? That happens here at 4, right? Because you get that 1/16, which is the first time that 1 over 2 to the n is less than a tenth. So what we would say here is that we need n to be equal to 4, but as long as it's equal or bigger than 4, then we're guaranteed. Okay, so as long as n is equal to 4 or bigger than 4, then we know that a sub n is within 1/10 of 5. So let's do a couple more. What if we wanted to make the terms of the sequence even closer? So how far or how large would you have to make n to be sure that a sub n is within 1/100th of 5? So again, that will mean that a sub n minus 5, we want that to be less than 1/100th. And as usual, that boils down to plugging in our actual formula there. So now it boils down to, well, when is 1 over 2 to the n less than 100th? And even here, I think we can use this table here on the left. 1 over 2 to the n is less than 100th. Right here when we get to 7, right? That's 1 over 2 to the n. So we would need n to be bigger than or equal to 7. And as long as you do that, you know that you're within 100th. So you're a distance of 100th or closer to 5, as long as n is bigger than or equal to 7. And lastly, how large do you have to make n to be sure that a sub n is within 1,000th of 5? So again, that translates to this. And replacing a sub n with its actual rule, we get this, and so it boils down to when is 1 over 2 to the n less than 1,000th. Well, our table's not going to help us here, but we could probably do it mentally, or we could just extend the table a little bit. So if I make this an 8th, well, actually, we can even just do it out. We know, hopefully at this point, you get that 128 is 2 to the 7th, so that must mean that 2 to the 8th is that times 2, which is 256. 2 to the 9th would be 512, and 2 to the 10th is 1,024. So that means we would have to go all the way to the 10th term. So as long as n is bigger than or equal to 10. So the point that's underlying all this, or the concept that's underlying all this, is that no matter what they give us, like let's say they gave us the numbers they're giving us here are a 10th, a 100th, a 1,000th. No matter what they give us, we can always go find an input value, which was 7 in part B, which was 10 in part C. We can always find an input value that will get us as closer to 5 than that distance here. Okay, so in like the limit definition above, the E is this. The 7 is the E, the 10 is the E. Right? The L is clearly our 5, and the D, that distance that they're giving us, would be that and that. And so if you go back and read the definition, or the limit definition again, it'll probably make a little more sense now. No matter what distance they give us, we can always go out far enough in order to get as close as we want. And that's really the concept that's underlying all this talk about limits. Okay, and I have a graph here just to kind of give you, to let you see it's a graphical representation what we mean. This here is 5, and I've graphed the function f of x equals 1 over 2 to the x plus 5, and all those dots would represent the terms of the sequence, and you can see that, so this is 5, this here is 5.01, so that's 5 and 100th, right? And you can see that if we want to get within 100th of 5, this visual tells us that we need to go out, so that 7th term is just right below it. We'd have to go out to the 7th term at least, and then every term after that will also be within 100th of 5. Okay, so no matter what distance they give us, we can go out far enough. In this sequence to get within that distance, and that's what we mean by the limit being 5. Okay, so this is just a very brief, informal understanding of the actual rigorous approach to limit definitions. But just keep this in mind, and hopefully this helps when you go on to learn the formal definition in calculus. This will hopefully give you something to at least ground your understanding in.